Welcome to Statistics 101. Today we will talk about expectation values for continuous random variables. So let's begin. You all probably know Wilfredo Pareto and have heard about the infamous Pareto principle that says 80% of the consequences come from 20% of causes. Probably you know the statement from different contexts, like economics where a small number of rich people own most of the wealth. And indeed, Wilfredo Pareto got this insight from observations of the population and their relation to wealth. In particular, Pareto had a look at Italians' population's wealth. By the way, this image was taken from Wikipedia, a link to it's given down below in the comments. Okay, anyway, but what has Pareto to do with a continuous random variable? Or with the expectation value? So, the topic today will be the Pareto principle, because I think it is helpful when learning a new topic to get an association to another interesting topic. Well, let's see. At least there exists a distribution which is named after Pareto. The Pareto distribution, which is a power law distribution, and power law distributions are very interesting family of distributions that are very suitable for the description of occurrences of events or resources at different kind of scales. For example, the Pareto distribution was used for the modeling of extreme wind analysis. If that interests you, I got a link to the research paper for you in the description. The distribution has the following definition. We got a function f that depends on a continuous random variable x, and for each realization we got the following description. If x is larger or equal to some constant xm, the function is equal to alpha xm to the power of alpha divided by x to the power of alpha plus 1. And when x is smaller than xm, then it is 0. Over here we also have a plot of a Pareto distribution. The plot has the following parameters. Alpha is equal to 1 and xm is equal to 1. So as you can see, the distribution is 0 when x is smaller than xm. Other than that, our distribution decays and has a very long tail, slowly converging to 0. Use cases of a Pareto distributions are very variable. It is used in economics, in finance, in computer science and many more fields. Economics and finance are very common areas. But I think the applications in computer science are very interesting, like the modeling of network interactions. There's actually almost no field where you couldn't apply the Pareto distribution. So it's a very important distribution. So without further talking, let's dive into the calculations of the expectation value. So how do we compute the expectation value? Well, it can help when we think about the discrete case. In the discrete case, we would have a probability mass function and would sum the probability mass function times x over all x which are in the support. So in the continuous case, we are substituting our discrete sum with an integral and would integrate over x. And inside of our integral, we got our probability density function times x. So very similar, here we will integrate over the support of x. Over here, I wrote the distribution again so that you don't forget how it was defined. So let's start with a computation with a generic alpha, but we are interested for the case alpha equal to 1 for the time being. So the computation goes as follows. So we integrate over all x which are in the support, and we integrate x times the probability density function. This is equal to, now we know when x is smaller than xm, it is 0. So we integrate from xm to infinity because that's the only contribution which is not equal to 0. So we have x, and when we substitute the PDF, that's it. Then further down on the second line, it's equal to the integral x times alpha times xm alpha, and when we rewrite 1 over x to the power of alpha plus 1 to x to the power of minus 1 minus alpha. And then what we can do is, on the third line, what we did, we simplified this integral a little bit, so we put alpha and xm alpha in front of the integral, since this is a constant, times, and then we do the integral from xm to infinity over x to the power of minus alpha. Why x to the power of minus alpha? Well, because we have x times x to the power of minus 1 minus alpha, and x and this 1x, when we multiply it with the other x, the minus 1 in the exponent is gone. So we have x to the power of minus alpha, this is 1 over x times to the power of alpha. And this is equal to alpha times xm to the power of alpha when we do the integral. So when we integrate 1 over x to the power of alpha from xm to infinity. So let's do first the integral itself. What we get is x to the power of 1 minus alpha divided by 1 minus alpha. That's it. And now, since we are interested in alpha equal to 1, we have to see that 1 over 1 minus alpha, so we have 1 minus alpha in the denominator, this converges to infinity, right? Because 1 minus 1 is 0 and 1 over 0 is infinity. So what would happen for alpha being smaller than 1? Well, the limit again from x going to infinity for x to the power of 1 minus alpha, so 1 minus alpha, and if alpha is smaller than 1, this would be x to the power of some positive exponent, and this would converge to infinity. And so we can see that for alpha being smaller or equal to 1, the expectation value is not defined. So when is it defined? Well, it's defined when alpha is greater than 1. Let's start from the last line and do the computation again. So now, since we know that it cannot be infinite, so that the result will not be infinite, we can further simplify our expression. So we have the expectation value on the second line. Now we can insert the boundaries, and when alpha is greater than 1, then we get the following. The limit of x to infinity for x to the power of 1 minus alpha, for alpha being greater 1, is converging to 0. So the first term is 0, minus to the power of 1 minus alpha divided by 1 minus alpha. And now we can simplify, and what we obtain is the result. It's alpha divided by alpha minus 1 times our constant xn. So as we can see, the expectation values for alpha greater than 1 defined. And what are some observations we can do? Well, when we plug in, for example, alpha equal to 2, our expectation value is equal to 2 times xn. Or if alpha is equal to 3, it's equal to 3 over 2 xn. So we can see the expectation value is quite large in comparison to distributions like, for example, the normal distribution. And this is because the Pareto distribution has so-called fat tails, meaning that the right tail that we've seen on the plot here is extending over a quite large range over the x-axis. And that will give us a very large contribution to our integral, and that's why our expectation value will be larger than usual. So I think now we are ready to go over to the formal definition of the expectation value of a continuous random variable. So the definition goes as follows. So let x be an absolutely continuous random variable with a PDF fx. The expected value is, so the expected value is defined as equal to minus infinity to infinity x times the PDF integrated over dx. Given that, the integral from minus infinity to infinity for the absolute value x times the PDF dx is smaller than infinity. And this requirement is called absolute integrability. And what it does, it's actually a very common thing to do in mathematics, because it guarantees that the expected value is well defined. It's a handy requirement because there are distributions like the Cauchy distribution where the expectation value can be ambiguous. And when we got this requirement, our expectation value is well defined. And as an encore, let's see how the Pareto distribution relates to the 80-20 Pareto principle. Or does it even relate at all? And indeed, the Pareto distribution reflects the 80-20 Pareto principle. If alpha is equal to the logarithm 4 of 5, which is approximately equal to 1.161, so the expectation value is equal to log 5 over log 5 over 4 times xr. How can we see from that this reflects the Pareto principle? Well, for that we will need the Lorentz curve. I will not derive it here at this point, but it can be derived with the help of a Pareto distribution. The Lorentz curve is a function with an argument f and is defined as 1 minus f to the power of 1 minus 1 over alpha. And the Pareto principle states that, for example, 20% of all people get 80% of all the wealth. In reality, these are not the correct numbers, and it also depends on the country, of course, but this just serves as an example. So we can do an equation where we say that L of 0.8 needs to be equal to 0.2. If we solve this equation after alpha, we get our desired alpha. Why does the Lorenz curve help here? Well, because the Lorenz curve shows the disparity of a distribution. This can be a wealth distribution or something else. I hope this video was insightful, and if you got questions regarding expectation values for continuous random variables, please write a comment, like and subscribe, and I see you in the next one.